Introduction from me. My name's Paul Smith. I'm Application Support Engineer at IQD Frequency Products in the UK, and IQD has been part of the Worth Group since 2017. So a quick agenda. What we're going to cover today is why we use Quartz, including some information on Quartz processing, some information on specifying Quartz crystals, particularly with regards ESR, specifying Quartz crystals, oscillators, some noise performance, and also looking at designing a new device, including some information on crystal and oscillator modeling. So first of all, why do we use Quartz? Well, Quartz is a crystalline form of silicon dioxide, sometimes known as silica, rather like sand on the beach. And Quartz is used because of its piezo-electric properties. This is derived from the Greek word and means to press. By applying an electrical signal to the quartz, we can get it to resonate at a frequency depending on its dimensions. This resonant frequency provides the basis for an accurate electronic timing signal. As you can see from the little animated GIF there, by stretching and compressing the quartz becomes polarized, and we use this basis for our quartz devices. However, when we think of quartz, I have to advise that natural quartz isn't used anymore to produce frequency products. We use synthetically grown quartz. And synthetic quartz is grown in a device called an autoclave, which is a high pressure, high temperature container where the quartz bars chemically grow over a number of months. As you can see from the two photographs, the photograph on the left is for natural quartz. It's the sort of thing you would see in perhaps a jeweler's. The photograph on the right shows synthetically grown quartz and how it comes out of the autoclave. The natural quartz, as you can see, is quite what we call milky colored, and it has lots of impurities which we don't want. And so nowadays we grow the quartz, as per the picture on the right. It's very, very pure, which is what we need. Now that we've grown our lump of quartz, we need to cut it up. And the quartz bar is actually cut into slices called wafers. And the quartz is usually cut at an angle called an AT cut, which is the commonest cut used. You can see the diagram on the top. That's a picture of a natural piece of quartz, a synthetically grown quartz. And you can see there are lots of different angles of cut we can use. The little piece in the yellow shows the AT cut. After we've sliced the quartz, the cut quartz is then processed into round or rectangular parts and is now termed a blank. And these blanks are then processed and ground down to the thickness required for the specification required. And the two photographs you can see there, on the left we have rectangular piece of quartz, and on the right, circular piece of quartz. The rectangular quartz is generally used for small surface mount devices, whereas the round blanks tend to be used for lower frequencies and much larger through-hole devices. Once we've sliced our quartz and made our blanks, we then need to process them. And this diagram shows a quick cut down version of what happens. So as you can see, we've grown our quartz, we've sliced it up, we've processed it into blanks. We now need to add some metal electrodes. So working down the diagram on the left, we start off with our processed blank. It's then etched and cleaned to remove any impurities. We then have to apply some metal electrodes to give us our electrical contacts for the device. The base plating material is normally silver. That's the commonest metal that's used. Sometimes gold, but generally it's silver. Once the electrodes have been plated onto the quartz is then mounted into a holder. It then is adjusted to frequency, and the frequency is adjusted by removing or adding electrode material. We then place a lid on the device, it's sealed and tested. And that gives you a quick summary of the process of what's involved. As you can see the photographs on the right, the top photograph is a low frequency circular piece of quartz. It has two metal electrodes on, one on each side, and these give you the electric connections for your circuit. The photograph in the bottom right-hand corner is a rectangular piece of quartz. Again, it has silver electrodes on both sides of the quartz, but is a different shape and is used for much smaller devices. We now come to the key parameters you need to specify for a quartz crystal. For those of you who are not sure on crystals, sometimes it can seem like a bit of a black art, but there are a basic number of parameters you need, and for a crystal there are 6 key things we need. First of all, of course, we need the frequency. It's the nominal frequency you require. It may seem a silly thing to say, but occasionally customers do ask us for crystals without knowing the frequency. So of course, as you can appreciate, this is the most critical thing. We then need the package. So this can be a size. It can be a small surface mount device, 3225 millimeters, for example, or it could be a through-hole type, such as an HC49. After that, we now come to the electrical specification, and there are 4 bits to this. First of all, we need what's called the frequency tolerance, and this is a measure of the accuracy at room temperature generally being 25 C. We then need a figure for the frequency stability, and this is a measure of how the frequency changes with temperature. We would need an operating temperature range. There are some examples there. And finally, we need a load capacitance value. And this value is what your circuit should present to the crystal. So those give you the 6 basic things we need. This little diagram gives you a rough outline of how the specification would look on paper. So again, we have the frequency, in this example, 10 megahertz. We have a package type, HC49, and we then come to the electrical spec. The first figure is the frequency tolerance. So in this case, the 30, it means plus or minus 30 ppm, ppm being short for parts per million. The second figure is the stability figure over temperature. This example is plus or minus 50 ppm. The temperature range is self-explanatory. It's industrial, it's minus 4085. And the last figure is the load capacitance. In this example, 16 picofarads. And that gives you an outline of the basic information we'd need for a crystal. So as I said, the frequency tolerance defines the frequency accuracy at room temperature. And this tolerance value is set during manufacture, as I stated previously, by adding or subtracting electrode material. However, the quartz crystal only oscillates within this tolerance value if the external oscillation circuit provides the correct load capacitance value to the crystal. You can see some typical values that you might see for a crystal tolerance. Plus or minus 10 parts per million would be considered quite a tight or low value tolerance, whereas 100 ppm will be considered quite wide. A typical value may be 20 or 30 ppm. Next, we come to the frequency stability. Don't be frightened by this graph. This is just an example of how different cuts of quartz behave over temperature. Generally, as I said before, most crystals are cut what's called using an AT cut. And that cut angle is relative to the Z-axis of the lump of quartz. And by varying that cut angle very slightly, we can get different performance over temperature. And these different colored curves on this graph give you an indication of what happens by changing the cut angle by very small amounts. And you get different characteristics over temperature. So when you as the customer specify you need plus or minus 30 ppm at minus 4085, then we as the manufacturer choose the most optimum cut angle to achieve that performance. The red box that's superimposed over the graph just gives you an indication of what cut angles can be considered if the spec required is plus or minus 20 ppm over minus 4085. So as you can see, some cuts fall outside that range and would not be suitable. And as the stability figure reduces, the number of cut angles that you can choose reduces accordingly. Finally, we come to the last figure for a crystal, the load capacitance. And this is the one area which generally confuses the most people. The low capacitance really is the value of capacitance that the crystal C wants to see in the oscillator circuit so that it's at its optimum frequency. You can see there's a little formula there for calculating the load. And it's a series combination of the two external capacitors plus the stray capacitance on the board. Now, generally, you cannot measure the stray capacitance in your circuit, so we generally start with an estimated value. And we generally choose a value between 2 picofarads and 5 picofarads as a starting point. And then you find that changing the values of the external capacitors, denoted here by CA and CB, will move the frequency up and down to optimize the frequency accuracy at room temperature. For you as a designer, this may need some experimental work. You can calculate a typical value, start with that, and move up or down in values depending on how accurate you need to be and whether you're too high in frequency or too low in frequency. The diagram on the left is a typical Pierce oscillator circuit. The inverting buffer shown and the feedback resistor is generally built into most microprocessors nowadays. So all you generally need to do is apply an external crystal and 2 external capacitors. Moving on from the 6 basic parameters that we need to specify a crystal, there are some other values that occasionally come in to play as well, and I've just listed a few examples here. The first one is ESR, or equivalent series resistance. So low values of ESR are sometimes specified on integrated circuit data sheets. For example, a crystal might have a standard limit of 100 ohms max, but the IC needs 60 ohms max. Some applications need a particular aging spec of X ppm for Y years. You may have another application that needs the crystal to be pulled, i.e. the frequency of a crystal can be changed by altering the load capacitance presented to the crystal. The pulling obtained is mainly dependent on the size of the quartz and the electrodes. Another extra parameter may be drive level. You have to remember that small crystal packages generally have low drive levels, but sometimes the IC used may apply a drive level above the device's standard limit. A crystal may have a standard drive of 100 microwatts, but the IC you're using specifies 200 microwatts. For any of these, please come and contact us to discuss any non-standard values you need. Most of these parameters can be accommodated. I wanted to touch also on ESR again. ESR has become a common discussion point and it's quite a hot topic. The number one thing you have to remember is applications shrink, and thus crystal packages shrink, the maximum ESR value increases. So it's important to have enough gain in your oscillator circuit to overcome increases in ESR. On IQD datasheets, we specify the maximum ESR for a given frequency range. However, in practice, the typical ESR value is generally lower than the maximum value. We are able to discuss any non-standard ESR values you may require, so please come and talk to us. The diagram on the right gives you an idea of how the ESR changes for a 30 MHz crystal with different package sizes. On the left, you can see for a 7 by 5 millimeter package, it's about 40 ohms max. As you shrink the package size to 1612 millimeters, the maximum ESR goes up to 100 ohms. So as you can see, if you need to change crystal type and reduce the package size, you need to make sure that your oscillator circuit has enough gain to overcome increases in ESR, and that's particularly important. Sometimes it becomes a problem if you just try and do a complete shrink of everything, the circuit doesn't work how you think, so please check this. We now come to clock oscillators. As I'm sure you all know, an oscillator is a quartz crystal mounted together in an IC in one package, and the IC contains the additional circuitry needs to make the quartz crystal resonate. You as the customer only need to apply a supply voltage and the device provides an output signal at the frequency required. The diagram on the right gives you an idea of how the device is constructed. It consists of a ceramic leadless chip carrier package with an IC mounted inside. The quartz crystal with the electrodes we discussed is mounted above the IC, and a metal lid is sealed on top. That device then becomes a complete unit and gives you a waveform as per the examples, whether it's square wave or sine wave. A quartz oscillator also has 6 key parameters, slightly different to the crystal, but similar. Of course, number 1 again being the frequency, the nominal frequency you require. Number 2 again is also the package, whether it's a size in millimeters or a type such as joule in line. Number 3, we need the frequency stability. As I said before, this is a measure of how the frequency changes with temperature. It's slightly different from a crystal in that in the frequency stability value, we generally combine the tolerance value of the crystal and the stability together, i.e. plus or minus 100 ppm. Again, we need an operating temperature range. There are some examples there. Commercial, maybe minus 10 to 60, down to industrial, and beyond perhaps to automotive. You also need to specify the output type. So do you need a standard square wave such as HCMOS? Do you need clip sine, 50 ohm sine, LVDS, LV Peckel? There are various output types for oscillators, and we have many in our product portfolio. And finally, we need a supply voltage. Each of your applications probably works at different supply voltages. Historically, 5 volt was very common, but it's becoming rather unusual nowadays as people reduce their supply voltages. 3.3 volt is currently the commonest, and we have devices down to 1.8 volt supply voltage. This screen shows you an example of how a clock oscillator specification would look. Again, we have the frequency, in this example 40 megahertz. We have a model type. I've chosen an IQD type IQX0791. You can look that up on our website. We have an output type. In this case, it's a square wave, HCMOS. We have a value for stability over temperature range. In this case, it's plus or minus 50 parts per million. The operating temperature range, again, minus 4085, and a supply voltage. And that gives you the basic construction of a simple clock oscillator specification. If you have all that information, then you're probably 95% there to specifying what you need. As regards oscillators, another key thing nowadays is oscillator noise performance. And it's a very common criteria required for an oscillator. As I'm sure you all know, all oscillators produce frequencies other than the main response. And a way of showing this graphically is with a phase noise plot, as the example on the right. So IQD, we can measure phase noise for frequencies over 10 megahertz. It's also useful because at the same time we measure jitter, phase noise being noise in the frequency domain, whereas jitter being noise in the time domain. So if you have an application that is critical regards phase noise performance, then please come and discuss that with us. Now that you've got a bit of information regards crystals and oscillators, the next thing is you're designing a new device. What are you going to use? There are the proverbial swings and roundabouts with each device type. So for a quartz crystal, generally it's low cost. An oscillator is slightly higher than a crystal. However, a crystal requires an additional oscillation circuit. The oscillator does not, because it's self-contained, as we already discussed. For a crystal, you as the customer have to design the oscillator circuit. You as the customer also have to build extra circuitry, and the component count on the PCB is generally higher. However, for an oscillator, there's no circuit design required, it's a lower component count, and less design knowledge is required. So for a crystal, it's a cost offset between that and design knowledge. For a crystal, do you have the time and knowledge to do this? Whereas generally an oscillator is plug and play. Only you as the designer can make that choice. It depends what's critical in your application. Most microprocessors nowadays can use either. They have the facility to use a crystal, or you can clock them directly using an oscillator. So you're designing a new device. Hopefully you've chosen which route you want to take, a crystal or an oscillator. First of all, do you have an existing full specification requirement? What is the application? Is it commercial, industrial, higher environmental? These are things which we like to discuss with customers, and we can guide you on what you need for the specification, and we look at that in combination with what the application is. Obviously, if you're producing things like low-cost toys, where the spec is quite wide, then that's quite easy. If you have higher environmental specs, such as downhole, then we have to look at different devices to survive that environmentally. We also have a facility on our website regards integrated circuits. So if you have a IC manufacturer or an IC chip type, then we have a search facility on the IQD website where you can enter either the manufacturer or the chip type to see if we already have parts approved with that device. And that's quite a useful function. Finally, what are the critical parameters you need to meet? Is it frequency? Is it package size? Is it stability? Is it temperature range? It may be a combination of all these, and sometimes some parameters have to be relaxed in order to accommodate other devices. But as part of our discussions, please come and talk to us about that. If you're choosing to use a crystal, some customers like to do crystal modeling. So if you need to do electrical modeling of the crystals, then we can provide motional parameter values. So you may need values for shunt capacitance, motional capacitance, motional resistance, motional inductance. And we can also provide values for trim or pullability, which is altering the crystal frequency, measuring the frequency tolerance at offset low capacitance values, or Q values, which is a measure of crystal activity. So if you're doing electrical modeling, we can measure devices and give you actual numbers for your calculations. You also may be doing physical modeling, and IQD is able to provide step files for 3D mechanical modeling of both crystals and oscillators. Many of our standard models already have step files on our website. But if there's anything there that doesn't, please come and ask us, and we can provide this information for you to do your mechanical modeling. IQD has a large product portfolio, so if you're having supply issues or need another source, then please contact us. Over the years, we have cross-referenced many competitive parts, and we can support equivalent specs from our product range. We have many custom design parts, and it's also possible if they're technically and commercially feasible. If you have any requirements, please contact us. As you can see, that covers the basic information you need for crystals and oscillators. It was short and sweet, but hopefully it gives you some guidance on what sort of values you need, what you need to take into account, and any extra things you need, whether it be ESR or modeling, etc. Please contact us.